For those of you who have just joined us, welcome to our webinar. Just some housekeeping items. As I mentioned, this is going to be recorded for anyone who has coworkers who maybe weren't able to join. We will post this onto our YouTube channel later this week. We will ask that everybody hold your questions until the end of the presentation. If you do want to type your question into chat throughout the presentation, go ahead and do that, but we will try to get to those at the end of the presentation. We are scheduled for an hour and a half, so this is a little bit longer than our normal webinar. So if you have a question and you're not able to ask it before you have to hop off, you can either email that over to us or you can type it in the chat, and then we can also, send that back to you after the webinar is over. So without further ado, I'll go ahead and pass it over to Garrett, who is our speaker today. Garrett, go ahead.
Thanks, Sarah. Appreciate it. And welcome, everyone. Thanks for joining today. Like Sarah said, my name is Garrett Lamb, and today we'll be exploring nuclear energy's powerful resurgence as a key solution to the 21st century challenges like climate urgency, exploding electricity demand from electrification, AI and data centers, grid reliability, and energy security. So over the next 90 minutes, we'll cover a high-level full picture of nuclear energy from its history, technical strengths, economic and geopolitical benefits, honest challenges, cutting-edge innovations, global trends, its essential role in net zero pathways, ongoing debates, and a realistic future outlook. My goal today is to inform you with a balanced view so that you can engage in discussions about nuclear's place in our energy future. With that, we will jump into the agenda. So the objective today is that you will leave with an understanding as to why nuclear energy is experiencing a global comeback and why it is such a hot topic in the energy industry. This is backed up by data on its low emissions, unmatched reliability, and energy density. We will examine modern advantages over older designs, honestly address barriers like cost and perception, highlight breakthroughs like small modular reactors, also known as SMRs, that promise a faster and cheaper deployment, review what's happening in major economies from the United States policy shifts to China's rapid builds, and position nuclear as a complementary baseload partner to renewables in achieving the net zero goal. The structure of this presentation follows in a logical manner. We start with the context, we build the case from nuclear, confront challenges head on, showcase innovation, survey the world, discuss integration and debates, then project forward with realistic scenarios from the International Energy Agency, also known as the IEA, and International Atomic Energy Agency, known as the IAEA. Please save your questions till the end, as we have a lot of information to cover, as Sarah mentioned in the beginning. We'll try to have time towards the end. If not, I will also provide my email on the closing slide. But with that, we will jump in. Okay, so the historical context of nuclear. Nuclear energy's story starts in Germany in 1938 with the discovery of nuclear fission by German chemists Otto Hahn and Fritz Strassmann. The use of nuclear energy starts in the 1940s with wartime fission research within the Manhattan Project, then transitioning to the peaceful power through Eisenhower's 1953 Atoms for Peace initiative. The 1960s through the 1980s saw explosive growth. The United States alone added over 100 reactors, as nations sought reliable, affordable baseload to deal with the oil and gas crisis. Nuclear plants have delivered high-performance generation for decades. Decline hit after the 3 Mile Island in 1979, Chernobyl in 1986, and later Fukushima in 2011. Combined with rising costs for stricter regulations, long builds, and cheaper gas and renewable options. Many historical boom and busts explains today's renewed momentum as old concerns are addressed and new needs are emerging in today's grid. So the current global energy landscape. As recent data from the International Energy Agency's Global Energy Review in 2025, fossil fuels still dominate at nearly 60% of the global electricity, with coal being the largest, but declining. Renewables hit 1/3, led by hydro, wind, and fast-growing solar. Nuclear contributes a steady 10% of electricity, but with record output in 2025 of over 2,600 terawatt hours. Clean sources together research reached 2/5 for the first time. Electricity demand grew over 1,200 terawatt hours in 2025, which is up 4%, far above historical averages, fueled by EVs, heat pumps, AI, data centers, and developing world industrialization. This creates urgent needs for reliable, low-carbon base load, which is exactly where nuclear power excels and why it's needed in today's power grid. Nuclear's comeback is driven by interlocking crises, climate science, and regulations that demand slashing emissions per the Intergovernmental Panel on Climate Change, or known as the IPCC. Pathways that rely on low carbon and firm power. Exploding global electricity demand is up over 4% yearly and growing, with data centers alone projected to double electricity consumption in many regions. Renewables grow fast but are variable. The world's grids need reliable baseload to avoid blackouts and backup fossil fuel peakers. Geopolitically, nations want independence from volatile oil and gas markets. New policies reflect this. The United States Infrastructure Act funding, the European Union taxonomy inclusion, and China's aggressive builds. Nuclear uniquely offers 24/7 low carbon power at scale. So the climate urgency, reliability, security, and demand is the main reason that nuclear has become such a forefront in the revival of power generation, as it provides a great base load as well as many other pros. Okay, so how nuclear power works. This is a simulation for a basic reactor. It's been simplified, so we'll have a simple look at how this basic pressurized water reactor, known as a PWR, operates. In a reactor core, uranium-235, also known as U-235, atoms split, causing fission. This is where the nuclear activity takes place. When it is hit by neutrons releasing heat, and more neutrons form a chain reaction. Heat warms coolant, which is in this case water, and in most designs is water, producing steam that spins turbines to generate electricity. This is just like fossil plants, but without the combustion. Critical safety layers include fuel cladding, reactor vessels, and containment building. A moderator such as water or graphite slows neutrons. The control rods absorb them to regulate. Today's modern reactors emphasize passive safety, which means no pumps and water needed for cooling emergencies. This is a big upgrade from older plants, as that there's no need for power to shut down and cool the reactor if things go bad. This is more reliable and a contained process, and it has powered the grid safely for decades with no leaks, issues, or any radioactive material escaping. Okay, so the advantage and climate emissions. Nuclear's full life cycle emissions, which include the mining of uranium, construction, operation, and decommissioning, are extremely low. Recent data puts nuclear at 5.1 to 6.4 grams of CO2 per kilowatt hour. When related to the IPCC's medium threshold at 12 grams, which is far below coal at 800 plus grams and gas at 490 grams. And pretty much similar to wind that generates 11 grams, while edging out solar PV at 45 grams. In many scientific studies, this accounts for everything from fuel supply to waste management. Nuclear has collectively avoided massive emissions by displacing fossil generation. It's a proven on-demand decarbonization asset, which is essential for electrical generation across the globe. And many of you are probably thinking, why is there emissions? Why is the emission so high on renewables? Well, it's into the entire spectrum and life cycle of creating these plants. So to build solar farms, to build wind farms, there's a lot of diesel, a lot of concrete, a lot of, there's just a lot of emissions that are emitted in the construction, as well as the operation of these systems that a lot of people don't take into account. So that's been put into this study by the IPCC. So the generation itself seems relatively clean. However, a lot of things are overlooked as far as the waste, how much emissions it takes to create and construct these facilities, operate them, and so forth. So that's where all of these come into as well. Because I had the same questions. It's like, why is wind and solar so high in the grams? But it's the construction costs, it's the emissions that are put out in the front of the construction and what's emitted to create these plants. Hopefully that makes a little more sense as to why, the emissions even on wind and solar are a little bit higher than once thought. All right, so the advantages of reliability and baseload power. So the capacity factor measures actual output versus the maximum possible. This is where nuclear generation truly excels. Globally, in 2025, nuclear averaged 83%, up from prior years, with North America at around 90%. U.S. plants routinely hit 92 to 93%, as they are the most efficient in the world, which is far above the solar, ranging around 25%, or wind, which is between 35 to 40%. This means nuclear is a near constant power source, which is independent of the weather and allows it to provide essential baseload, which reduces reliance on backup solutions. High factors translate to more electricity from fewer plants, enhancing grid resilience, which differs from variables that renewables face. So as an example, nuclear power is not affected by wind, by sun, by night, any of these things. It's just a constant source. As long as the fuel rods are in the water making heat, you're going to have power generation. So that's pretty much what it comes down to. All right, so some big advantages is energy density and land use. Nuclear's fuel is incredibly dense. One uranium-235 pellet is equal to 1 ton of coal in energy output. So what they're saying there is basically it takes 1 pellet of uranium-235 to produce what a ton of coal will produce. So a ton of coal has the same energy mass as 1 pellet of U-235. Nuclear's land footprint per terawatt hour is tiny when compared to solar and wind. This efficiency means that nuclear plants fit on smaller sites while delivering gigawatts of generation by avoiding large-scale land consumption that also impacts biodiversity or farming or other uses of the land. Nuclear is ideal for land-constrained regions, higher density areas where land is fairly scarce. So it just takes up far less land, doesn't need as much, real estate to create as much, if not more power than wind and solar does. Okay, so some economic advantages. There's job creation, manufacturing, supply chain development. All of these come into play. Nuclear generation projects create many well-paying jobs, which include engineers, technicians, welders, and many other positions, which often lead to between 500 to 1,000 jobs during construction phase alone, and hundreds of permanent positions after plant completion. These projects also drive manufacturing of pressure vessels, turbines, and supply chains. Nuclear plants operate between 60 to 80 plus years, which provides decades of economic activity and predictable low fuel costs. Local economies benefit from not only the energy produced by the plants, but by the tax revenue and infrastructure upgrades. So not only does it help with cheapening power, it also provides economic growth for the community and surrounding areas. So energy security and independence. Unlike oil and gas that are specifically tied to volatile regions, uranium is an abundant source, with Australia, Canada, and Kazakhstan as top producers. These are many, there are many years worth of nuclear fuel across the globe, and nuclear consumes its fuel much slower and at a much more efficient rate than fossil fuel generation. Nations across the world can stockpile uranium for decades. This shields economies from price shocks and supply disruptions, as we've seen in the oil and gas industries due to their volatile up and down spikes. So geopolitical impacts and strategic advantages of domestic energy production. There are several nations taking advantage of nuclear generation. They leverage self-reliant energy, exportable tech such as reactors, fuel service, and influence in global clean energy. China and Russia's export strategy builds in illustrating this. Domestic focus counters over reliance on imported fossils, bolstering national security in an uncertain world. Okay, this is one of the big things that everyone looks at when they think about nuclear. It's the safety concerns and the public perception. Public fears of nuclear generation stem from these high-profile incidents. The 3 Mile Island that had minimal consequences due to its containment, Chernobyl's RBMK, or also known as the high power channel reactor design, lacked key safeguards, as well as human error amplified this disaster. Fukushima's backup system failed against an extreme tsunami. Fatalities surrounding nuclear incidents remain low relative to coal's air pollution deaths or even hydro dam failures, which are relatively minimal to null. I mean, they've happened. I'm not going to say they haven't happened, but as far as nuclear caused deaths, it's very low. Industry responded with rigorous international revenues and upgrades, which has led to modern plants being much safer. A lot more went into it, a lot of pros and cons, a lot of lessons learned. These three major catastrophes, caused industry, safety boards, everything to look at ways that we can contain radioactive material, contain all of the issues that could potentially happen. And in today's modern reactors, you'll see a lot of these lessons learned that have been implemented. So modern safety features. Now, for example, Gen 3 and Plus reactor designs incorporate massive safety and core cooling through natural forces if pumps were to fail. There are multiple redundant systems and robust containments in place to prevent radioactive releases. By employing a defense in depth layers such as fuel cladding, vessel, and building to ensure failures stay contained. These features make core damage probabilities lower than older nuclear plant designs. So the passive safety systems for nuclear energy plants, as you can see in this diagram, is contributed right off of those lessons learned from the three events that we talked about in the previous slide. There's still containment vessels, reactor cores isolated, internal condensing water. There's water film evaporation. It's more of a contained, enclosed, more efficient, safer reactor. So waste management and storage. Nuclear waste is relatively tiny when compared to that of coal, ash, or other byproducts. All United States commercial nuclear spent fuel could fit on a football field around 10 meters. high. So about 30 feet high on that football field, as you can see in the diagram. All of the United States nuclear waste could fit there, and compared with one coal ash pond, as you can see. Initially, the waste is cooled in pools, then stored safely in dry casks, as you can see in the top right. Work on site for decades with no issues. Permanent solutions like Finland's repository demonstrate this feasibility. Recycling, also known as reprocessing, can reduce the volume further and recover spent fuel to be used again. So the dry cask actually is something that was designed in the New Mexico laboratory to harness all of the radioactive material that they've created down at Los Alamos. So the dry cask has a sealed inner liner, has fuel rods sealed inside their inner cylinder. They have a fuel assembly. This is a really safe, robust way to store energy. Not to mention nuclear energy that is nuclear waste from nuclear power plants is much different than that of a weapon grade uranium, in the fact that it's not enriched half as much as weapons grade uranium. So the radioactiveness is nothing near weapons grade radioactive, even though that is kind of the public perception. It's quite a bit different. All right, so some economic challenges. The biggest barrier is upfront capital, with constructing plants costing billions per plant, with multi-year construction, amplifying financial costs, delay from supply chain, regulation, or first of a kind issues usually led to overruns in cost. This constraints with modular renewables, which have a much faster deployment. Some solutions include government-backed loans, standardized designs, and moving towards small modular reactors, or known as SMRs, to reduce risk. And we'll talk about those a little bit more coming up. But yeah, that's the big thing that that drives nuclear. Is there's a lot of economic challenges as far as cost, but there's also a lot of permitting, a lot of policy, environmental impacts. And as you can see, the timeline is the biggest issue. As far as constructing, capital is the second largest issue, and then the fuel costs relatively nothing. That's the thing, that once these plants are built, as far as generation is concerned, it really costs primarily nothing to generate it as far as a fuel source. I mean, you still have your overhead costs, employment, salaries, all those things, operational costs, but the fuel itself is relatively low. And just something to keep in mind there. Okay, so regulatory and permitting hurdles. Regulations ensure safety, but adds greatly to time and costs. The United States NRC process can take upwards to 5 to 10 years, which is an extremely long time. Additionally, environmental reviews and public input extend these timelines. So not only do you have the timelines it takes to get your processing, get the permitting, get it, going through that process, it can go out to public review, which can also make things a lot longer. Environmental impacts, all of these things can just add to a continuous timeline. In contrast, China has a much more streamlined approach enabling rapid builds. So in China, they don't have half of the regulations. They don't really participate in any outside, environmental impacts. They don't ask the community or public what their thoughts are. They just, if they want it, they go for it. This helps to building them speedy and new. That's also why China is looking at SMRs and the fact that they could rapidly deploy them even quicker at a lower rate and also have them scalable. Okay, so small modular reactors. Small modular reactors, also known as SMRs, shifts the traditional method of nuclear plant construction by moving towards a more streamlined process where the SMRs are built in factories, such as cars. They're shipped and assembled on site, which leads to cutting time, cost, and risk. So for example, they're built in a factory. they're shipped out, construction. It's a lot easier to relatively control costs, keep things from overrunning as much. You kind of have your set price of the item of the SMR. You'll have your construction cost. It's pretty much all within a bid process versus, going through and building. And, the big thing is with traditional plants, you have, anywhere from 5 to 10 years where you have to go through permitting and costs. Well, within 5 to 10 years, inflation, all kinds of different things can overrun original thoughts and costs, which just leads to overruns no matter how well you try to budget it. Where a factory built, relatively quick, efficient method like SMRs would definitely help with the cost, the speed, as well as the deployment. So the smaller size allows incremental additions that suit grid or off-grid uses. Many tech companies have invested in SMR technologies as a viable solution to power their power-hungry AI and data centers. The United States has several projects such as NuScale, TerraPower, GE, Hitachi, and Westinghouse, just to name a few, with many others continually emerging, helping to advance widespread global interest. As well as having the competitiveness of all of these working together, it's making the actual product much more streamlined, much better. They're learning from one another. It's a really interesting concept. We could actually have a complete presentation on SMRs just itself, its technology. It's very vast. It's very interesting. There's a lot of information out there. Very neat technology. All right, so advanced reactor designs. So these are considered the Gen 3 plus reactors, and it builds on decades of experience with major upgrades such as passive cooling, severe accident resistance, and simplified layouts that reduce parts and costs. New plants like the AP1000 demonstrates this. As you can see, you have your Gen 2, and then you have your Gen 3. Things are getting way more streamlined. You're not needing as much, but they're not taking away the safety. Safety is still a big concern, operational, but they're also being able to streamline things with new technology, new advancements, new engineering skills, new materials. All these things are helping to make these reactors more and more efficient with each version that's coming out. There's been a lot of research, a lot of technology, a lot of scientific and physics that have gone into a lot of those constructions. The Idaho National Laboratory, for instance, has spent lots of time working on these with the United States military for their aircraft carriers, submarines. That's kind of where the idea for SMRs came from. And it's been a technology that's been taking place, even though you haven't heard a lot about it in the media or anything like that, just because nuclear's kind of had this stigma around it that it's not safe, it's scary, these kind of things. However, the technology has been evolving in the background heavily. It's never stopped. It's just a resurgence coming now due to the new technology, the way that we can add base load, a better way to make sure it's safe, better perception to the public, all these things. So yeah, there's just been huge strides between each different version of reactor and different technologies, better ways to do things. It's an advancing and movable resource where at the core it's still fission, it's still nuclear fission, it's still using uranium-235, all these things. They're just figuring out more efficient ways to do it, like we have with our vehicles, all kinds of things. It's just an evolving technology, which is great and exciting to see. So the Gen 3 reactors, they serve with decades of experience with major upgrades such as passive cooling, severe accident resistance simplified. So you can see that within each one of these that there's also the core that contains, you have the outside shell, you have the reactor. There's a lot of safety that's going into. They're self-contained units. So if something was to happen, nothing's going to get out. That is the main goal. They don't want any radiation, anything to escape. much more thresholds, and these are built right off of what the learning, the lessons learned and the learning abilities from the three major incidents like 3 Mile Island, Chernobyl, and Fukushima. Carrying on, so generation 4 and experimental reactors. There's also been a lot of talk about the next generation experimental reactors that could even be higher efficient, basically reduce waste to almost nothing. They're fast breeder fuel, which is molten salt, potential sustainability, and they still are much more in development, but the technology is getting even more advanced to what we have right now. So the Gen 5 reactors aim beyond the fast reactors that breed more fuel than consumed. So in essence, they're creating just as much energy as they're consuming. They're just, it's a cycle of give and take. Molten salt designs operate in extremely high temps for efficiency and safety, with liquid fuel reducing the potential meltdown risks. These new type of reactors could recycle waste, which is their own waste, and extend resources. There are a couple of experimental designs right now that are being looked at from TerraPower and Moltex, just to name a few, who have made significant progress towards this deployment. It's still at the experimental stage, still a lot of science, still a lot of R&D that's going into it, but it is interesting. It's really cool that there's still more innovation to come with nuclear power versus the major innovative jumps that we've made so far. Okay, so fission energy. So fission fuels are light atoms like the sun. There is no chain reaction risks and minimal to no waste. Projects like International Thermonuclear Experimental Reactors, or known as the ITRs, aim for net gain while private firms accelerate research and development. This is a science fusion has been something that has been really highly talked about. It's promising. There's a lot of science, a lot of research going behind it, and it's actually accelerating with new advancements every year. As of now, a realistic demonstration for one of these plants might be ready in trial runs as soon as the 2030s. However, with potential to be more like the 2040s. So if this technology is determined to be successful and it can be harnessed and used, it could potentially lead to unlimited clean power, is what the goal is. Now, if we get there, that would be great. This is still experimental. We don't know yet, but they are making great strides towards fusion energy and making it work. So emerging technologies. So accident tolerant fuels, known as ATFs, can resist meltdowns much larger in accidents and much longer accidents. So they can take larger accidents and also keep things from happening much longer than standard materials that have been used in the past. So additionally with these ATFs is new alloys and ceramics that can handle much higher temperatures. Digital twins, AMI optimization operations can detect much earlier. So not just better materials, we also have better technology, better ways to monitor, better ways to understand how the system's actually working with new sensors, new SCADA systems, new technological learning that goes along with the actual physical device itself. These upgrades are being applied to existing fleets as of right now. There are several nuclear power plants that are doing trial runs on sensors, on different technologies to see if there's things that can be learned not only for generational growth and future technological advancements in nuclear technology, but better ways to safely update their systems, make sure that they're running at their peak, but in a safe peak, those kind of things. Just an awesome way that the industry's learning from one another. Not only is they're looking towards the future, there's also looking at what technologies that are now available can help with older systems. So it's a very interesting dynamic that's taking place right now with technology and science. It's really cool. So these major upgrades are being applied to these existing fleets. And also, they're being pushed out into the newer builds, like I said, which is providing better performance, going to provide better reliability, and most of all, it's going to provide better safety for the operators, the communities, and anyone else who has a bad perception of nuclear power. It's actually got a lot of safety built into it, and it's just getting safer with all of these advancements in technology. Not to mention, emerging technologies take a lot of power. That's a lot of why nuclear is getting a lot of focus. Is like we're getting all these technologies. As you can see, we've got we're looking into robotics. We have EVs. We have new high tech medical devices, data centers, AI, all of these things that are just power hungry consumption. The grid is growing. We don't have the generation right now to feed as fast as the grid is growing, as far as demand is growing. So it's really cool to see that technology and energy are kind of forming together, as well as bringing in that third trifecta of science to really put all this together and move it forward in a way that can basically help all three. It's really cool, really interesting. This is another sector of this we could go way deeper into, just as SMRs, emerging technologies we could go really deep into. We could get into all kinds of different things, different fusion, fission, how all this works, how these SCADA systems, how these controls and sensors, all these things. But anyway, just something to keep in mind, that this is a very technological advanced world we live in, and nuclear is no exception. In fact, nuclear is kind of at the forefront with this technological advancements. All right, so right now let's focus on the United States. Throughout the last decade or so, there's been bipartisan support, as there's been a need for power demand. Base load, as fossil fuels are coming offline, we're needing something to come in and replace the base load that is ever growing, continually growing, and is supposed to just keep growing at 4% or higher, depending on situations. And that's globally. That's not just in the United States. But anyway, the United States has shifted from relatively stagnation with nuclear technology to a bipartisan support through legislation for major funding for these small modular reactors, these SMRs, for research and development. Additionally, with research and development of advanced reactors and restarts of old plants. And that's something that gets talked about a lot. We do have plants that are, just sitting stagnant, that have, you can consider them mothballed, but they're not really mothballed. They're maintained, they're just not active. And there's a lot of interest in bringing those back, but bringing those back would also, and it's including the restarts, would be putting all of this new safety equipment in, the new technological advancements, all these things. So bringing back what's new, but making it better, safer. So it's not just firing up old technology, it's making old technology new and viable once again. Additionally, with research and development, there are several private sector tech giants, such as, you've probably seen on the news that Meta, Amazon, a few other big tech giants are looking into the SMRs and their feasibility as far as powering their data centers on site, due to their compact design, compact size. They could bring them right to their site, have their own power plants. There's been legislation put in place that is allowing these companies to actually build generation plants for this very reason. You know, nuclear power is reliable and clean, and that's a major thing that they're looking at. It gives a steady base load, which is exactly what these tech giants are needing. This new interest in legislation is aiming to rebuild capacity and export potential hugely. It's not widely known that nuclear is such a major topic in the United States. It is to some, but it's really gaining momentum, and there's a lot of good reasons why. And technology is really a main source of that push for more bipartisan support, for more generation growth. And the real scary thing is, demand's increasing and our generation with fossil fuels is diminishing. We've got to have something to go in place to put that base load back to a stable condition. Okay, so the European perspective. So Europe and France rely heavily on nuclear power for low carbon grid with plans to add more nuclear generation as demand increases. So France is all in on nuclear power. They have been. It's working great. It's working safely. They're loving it. They're wanting to build more. Germany's 2023 phase out caused energy peaks to rise and caused grid stability issues and security concerns within Germany and the UK and Europe as well. There's also been talk with Germany about possibly pulling back on this just due to that fact. That's just kind of a topic that's still being talked over there in Europe, and we'll see what happens. The UK has taken steps to advance nuclear reactors for their net zero goal as well. They're big into the SMR technology. They're really wanting to see what the United States can do. They really want in on the SMRs. Europe as a whole has shown a spectrum of different strategy when it comes to nuclear generation. With nuclear generation, there's a lot of things you can look at. You can bring your old plants back on, which they have in Europe, bring new technologies in, such as the SMRs. They're looking at it, but in Europe, they understand that nuclear is kind of their main climate-free baseload. So, kind of where they're at. China and Asia. China currently leads with dozens of new nuclear reactors added in recent years, with more currently under construction today. Nuclear power generation has become the backbone to China's large exports of technology, of tech globally. China is one of the world's biggest manufacturing giants, and in doing so, they need a lot of base load. They need a lot of energy, which is why they're relying heavily on nuclear, and they're continuing to add nuclear to their energy portfolio. Additionally, throughout Asia itself, nuclear power growth is in full steam ahead to meet the high demand for energy over there. While not all countries in Asia are working towards a net zero generation portfolio, many are, and nuclear generation fits this model perfectly for them. And you'll see that theme throughout a lot of discussions with nuclear power, is that the clean energy across the world is the main topic. They really like the idea of the strong base load, the energy consumption, the density of the energy itself, the smaller foot. There's a lot of pros towards nuclear. The biggest issue with nuclear is the perception and those major events that took place, which, there is reason to be skeptical, and it can be dangerous. But, there's also been a lot of steps put in place to make things a lot safer, work a lot better, and be more reliable. All right, so moving over to Japan. In Japan, the Fukushima event led to a pause in nuclear expansion. So after Fukushima took place, nuclear expansion in Japan had come to a standstill at that point. There was a pause. There's a big push to look into their nuclear system to see if it was something that they wanted to continue, to make sure that their systems were safe, what they could do to make their system safe again. However, it was quickly noticed that they can't do without nuclear. The pause did not last very long as nuclear plant restarts started to take place with an addition of new measures and standards in place to help to address the growth needs of Japan's goal of energy independence and their net zero emissions goal. Additionally, in Japan, the public support has grown heavily as benefits are being seen both in the cost of energy and their grid stability. So Japan has a very positive outlook on nuclear power as a viable source for their generation. It keeps costs lower, as well as making sure that their demand and they are considered energy independent from other sources like importing fuel and oil and gas, all these other thoughts. Plus, Japan doesn't have the major footprint that a lot like the United States, Europe, Asia, and all these for renewables. So the smaller footprint, it just makes perfect sense for Japan, and that's the way they're going forward, and that's how they see it, which is why they're pushing forward full steam ahead. All right, so emerging markets. So Throughout the world, developing nations are choosing nuclear power generation for better and more access to much needed energy due to many factors such as economic growth, ever-growing demand for energy, and climate goals. So much of the new nuclear growth has been funded through, vendor financed options that are funded through Russia, China, and Korea. A lot of these countries that are they're getting electricity for the first time, and they're wanting to generate, and they see nuclear power as one of their longest, as far as a long haul good investment for continued growth, because there's not a lot of funding, a lot of help there, but they know, they see the benefits in nuclear as more of a viable source than like fossil fuels and all these things, because they can't really deal with the volatile ups and downs and peaks with their gas and oil. They really want a steady power supply that doesn't fluctuate as much. And they are looking heavily into SMRs. A lot of these third world countries are looking to SMRs as their solution, and they're really hoping that they take hold and that they can jump on that bandwagon. All right, so net zero and climate goals. So the International Energy Agency, also known as the IEA, has aggressive goals in place for net zero by the year 2050. They've kind of looked at that goal. Can it be met? Can it not? As of right now, it's still standing. And a lot of this is due to the forward push from nuclears. They really do. The IEA really does see nuclear power as the future, and that most countries are going to jump onto it. Many scenarios show that nuclear capacity is growing significantly, around 800 to 100 plus gigawatts by 2050. This is their projection. Like I said, things can change, but as of right now, with the studies, the interest, all of what's going through, their studies are showing that it's going to be that significant of a growth within the next 20 years. With very ambitious projects to support a massive electrification fueled by ever-growing energy demand while additionally cutting emissions. Nuclear's power generation helps to fill the gaps where renewables fall flat. Nuclear is the answer to obtaining a stable, reliable net zero baseload globally. So as of right now, the only real solution to replacing fossil fuels is nuclear, and that's no secret. It's nothing that anyone's not really aware of. Nuclear is definitely going to be the answer to fossil fuels, whether or not public perspective will glom onto that and see it for what it is. And it's true that there hasn't been a lot of communication, a lot of positive talk about nuclear energy as a whole. There's a big stigma around nuclear energy. It's unsafe, it's unstable. You have all of this radioactive materials. We don't want that in our communities. We don't want that in our back doors. I mean, there's just a lot of things that have plagued nuclear power, where with the science, with the new safety coming forward, that perception is beginning to change, and there's been a real push to show. There's been a real push to show how viable nuclear power is, how safe it is, what the benefits are versus just the fear that it's been pushed before. So it's very interesting that dynamic has changed. But we have a lot of things to thank for that change, and the fact that our growing demand is just increasing. It will not slow down. There is absolutely no choice when it comes to generation. We need to build generation, and it's going to happen. Whether it's nuclear or not, we've got to have generation. So nuclear definitely has a place. Whether or not it will be glommed onto, like the Energy Agency, the International Energy Agency, and the International Atomic Agency are thinking it's going to, as well as how governments are starting to respond to pulling back red tape and regulations on nuclear, as they are seeing that this is potentially a much more viable source now than it was before. There's a lot more safety measures. There's a lot more technology in place that can trigger issues way before it ever gets to a point that there would be a meltdown. There are so many safety triggers in place now due to technology, with different sensors, with different technology, training, all this stuff. Technology has made nuclear power so safe. It's just incredible. I mean, the technology advancements have made nuclear such a viable source now that people around the world, governments, they just can't ignore it at this point. And that's why it's really growing. There's just a lot of demand for it, a lot of need for it. It's definitely the solution to the baseload problem as fossil fuels come offline. And it's no secret. They can definitely tell that. And that's why you're seeing a shift in the global markets towards this. There's also been a lot more buying and stockpiling of U-235. So uranium is being purchased. It's kind of interesting. You can actually buy uranium on Amazon. The big thing with uranium is it's not enriched uranium. You can actually buy uranium on Amazon. I actually have a couple pieces, and you can actually put it in your hand and you can feel the heat off of it. It's not, there's a little radioactivity, but nothing more. Your microwave puts off way more radioactivity than anything that unriched uranium. So it's kind of interesting. Uranium is heavily abundant. The United States is starting to stockpile it. Canada has been huge in the SMR movement. They are really wanting to move forward. They believe that it'll be the main goal for Canada is to go to nuclear because they have a lot of solar. I mean, they have a lot of water. They have a lot of hydro. They're just nuclear is Canada's main goal right now, and they're not. And there's no secret about it. They have done a lot of advancements in technology and have funded a lot of the SMR work as well with NuScale. It's been a global look with SMRs. So anyway, moving forward, so like I was saying before, it's complementary with renewables as their baseload. So nuclear generation runs flat and constant. So it is just constant. If the rods are in, they're making power, and provides reliability and safe and steady baseload to cover the demand and the ever-growing demand. While renewables deal with spikes due to environmental constraints, such as when the sun goes down or when wind is available or not available, snow, rain, all those things that can throw variables into solar and wind. Though the addition of battery storage has helped to flatten the spikes with renewables, nuclear power generation reduces the need for renewable overbuilds. Nuclear power is complementary to renewables in that it's clean, stable, and is the last piece to the climate first energy trifecta. So it's the last part to the net zero, and that's how the IPCC is seeing it as well. They're saying nuclear as the only viable choice for baseload at this point in time that will work with renewables as fossil fuels come out and go offline. So nuclear, it's steady. I mean, that's the thing. It's a steady baseload. It is, if you want it, it's there. It's on demand. It's there. It's now. Um, Low cost at peaks. That's the thing, that once the facilities are built, I mean, you can generally generate power at a fairly low cost compared to fossil fuels. I mean, you'll definitely have costs as any plant does with personnel, wages, all those kind of things. But as far as the fuel itself, it can even lower energy costs throughout the country and the globe by just by that steady state. All right, so today's modern grids are growing through the use of AI and smart tech that has helped tremendously with real-time load balancing. In renewables, battery storage has helped to smoothen and the drastic up and downs associated with them, while nuclear provides a firm and reliable base. With the need for more power and upfront costs, there are also hybrid solutions where nuclear and solar are going to be on the same site. With modern smart grid technology, it's becoming much easier to operate these hybrid systems within the same operational facility. So, and that's just it. I mean, you're going to see these SMRs in the future where they also have solar there as well. it's just not going to be as prominent, just due to the fact that nuclear can generate so much more power. They have much more energy dense resources. But hybrid facilities are something that they're definitely looking into. There's a lot of plans in it. Europe is heavily looking into hybrid systems, just due to the fact that there's the SMR technology is still fairly new, and there's still kind of there's questions there, even though that it's been very viable and it's been proven to work, and it's definitely a promising technology. Um, hybrid systems are definitely something that a lot of countries and a lot of companies are looking into. With the grid modernization, just like anything, it's helping with technology. You're being able to see the grid. You're being able to see the system. You're being able to see your electric system, your generation, your transmission, all of these things at once. So it's just modernizing and making the grid way more compatible and a lot safer. More opportunities for growth, job wise as well. There's just it's incredible where the future's going, and nuclear is the main source that can make this technologically and power hungry future of ours happen. Okay, so the circular economy in nuclear. The new method of reprocessing and recycling spent fuel to recover usable uranium-235 helps to reduce nuclear waste volumes by close to 90%, which also extends the life and stockpile of the fuel used in nuclear generation. The new experimental Gen 4 reactors could enable a full cycle. As we had talked about in the previous slide, their goal is to make it to where the waste is used and it's just a full recycle. Whether we'll get there, I'm not sure, but it's a really cool fact and really cool scientific fact that they're working into. So this is just another way to advance circular principles for long-term viability when it comes to nuclear. So fuel recycling, processing spent fuel to recover unspent uranium. It reduces waste volume and extends resources. Closed fuel cycle potential in advanced reactors, which would be huge. It'd change the waste concern altogether. And then sustainability and boost. I mean, just the sustainability of nuclear and how it operates and how it's on demand and it's right there. I mean, it's just incredible technology, and I think we've kind of been behind the curve as far as bringing nuclear more into the grid and making it more available as we have in the past due to the negative public perception. Just in the fact that the technology works, it's proven to be safe. I mean, yes, there is definitely risk in nuclear as there is in anything else. There's just as much risk, driving your car each day, all those kind of things. I mean, you can't eliminate 100% of risk, but nuclear has pretty much gotten there with their technology as far as the harmful radioactivity that could get out. And like I said, the radioactivity from the uranium-235 that's put into nuclear generation is not the heavily enriched uranium-235 that's found in like nuclear bombs and those kind of things. It's not something that is super volatile. It's not enriched uranium like, a lot of like, because with the nuclear your bombs and things like that, what they're looking at is they need to enrich the uranium to get to a critical mass, to cause critical mass, to make, they want it a big bang right at the moment, where uranium-235 that's put into the nuclear power plants, it's just a steady warm, we're just basically warming water to create steam. That's all we're doing. We don't need it to be volatile. We don't need it to be anything like that. It is enriched to a point. I mean, it's not just like once you pull it out, I mean, it's not like it's not enriched a little bit. I mean, there is some enrichment that goes in place before it is put into reactors, but nothing compared to moving it to a critical mass. So for instance, if the plant tipped over, you're not going to have a nuclear explosion or anything like that. It's just the radioactivity that we want to make sure we look at, and that's why the containment has been so studied. The containment systems on the SMRs, that is one thing that they have right, is the containment system on there. They're self-contained. They're not gonna have leaks. Even if they were to have a meltdown, they are containing. They are working to contain anything like that. But like I said, with the technology and the sensors and the advancements and all these things that have taken place, the likelihood of a meltdown even occurring is slim to none, just due to the fact that there's quicker response time, there's quicker things that can happen, a lot more alerts, a lot more, with technology, you're seeing things way quicker than we ever did in the past. So, it's really cool. All right, so there's a cost competitiveness debate. Nuclear is high up front, but it has low operating fuel costs. Renewables and storage, they have low capital up front, system integration costs. However, there's talk about how that's changing and the fact that real estate's going up, across the globe, not just in the United States. Land is not cheap as well. So, I mean, it's kind of becoming a little more of a conversation with renewables as well. Long-term nuclear, it's a strong power value. It just adds way more value than any negative. System-wide economics, basically we're looking at a diverse mix. I mean, we're not looking at a grid that's going to be 100% nuclear. Absolutely not. There's places for nuclear. There's places for renewables. Absolutely. But with the diminishing of fossil fuel use, the volatility of fossil fuels, the cost that's going up and down that's associated with those, I mean, nuclear can definitely cause a stable base load at a stable price, bringing energy prices down, as well as providing a reliable and stable power grid. I mean, it's just incredible when you look into nuclear technology and generation and how many benefits there actually is. I mean, there has been a long series of debates regarding nuclear's levelized costs of electricity, or LCOE. Being higher. I mean, it's being higher due to the upfront capital, where renewables are much cheaper upfront, but need but need storage and transmission. You know, Nuclear definitely needs transmission as well. I mean, I'm not saying that that's not a cost that goes along with nuclears, but it's just something to think about. There have been many system studies that show nuclear adds immense value in reliability and reducing overall costs in high renewable grids. With the new small modular reactor, the SMR technology, this debate has become much more favorable in nuclear due to the low and more predictable upfront costs, the scalability, and a smaller facility footprint. So yeah, I mean, SMRs, like I said, we could do a completely another hour and a half presentation just on SMRs itself. The technology is really neat. We can talk about how it originated, all these things. It's really neat technology, and SMR technology has really changed the landscape when it comes to the look at nuclear. And that one of the reason is because nuclear plants up, the permitting, the licensing, all of those costs go in, plus the permitting and the licensing takes anywhere from 5 to 10 years. There's just so much uncertainty when it comes to costs with timelines like that. You have inflation, you have different costs, materials are changing. What was a good material 5 to 10 years ago? There's probably something better, but it might be more expensive. I mean, there's just a lot of variables when it comes to building a large scale nuclear plant. The costs are most likely going to overrun, like the new plant that was built in Georgia, the new nuclear plant that was built in Georgia. I mean, it went over astronomically in cost, but they still realized that the cost was well worth it in that long run, because the long run viability of nuclear power generation and the plant's longevity, kind of counterbalances that. But coming up with the initial cost for a plant that size is definitely something that not everyone can just do. And, having the backing is hard to get. There's things like that. But when you go to the SMRs, there's just so many possibilities. I mean, you can pull it in on an 18-wheeler, set it up, get it ready, plug it in, and you're off and running. I mean, it's nothing like, and you already know what it's going to cost. Build times between 1 to 6 months, depending. I mean, that's just a rough thing. I would definitely probably look more towards 6 months when they're fully scaled running, just due to the fact. But once the assembly line gets rolling, I mean, I could see it getting down to that 1 month threshold like they're advertising. They also have SMRs that are, the main ones that you're talking that are being advertised by NuScale and Westinghouse and all these other SMR facilities are between 30, 50, and 300 megawatts at the large. However, there are SMRs out there right now that are being that are being tested that are putting out 1,000 megawatts. I mean, 1,000 megawatt SMR would change the game tremendously. And you put a couple of those out somewhere, I mean, you're generating a good amount of power. And it's, it's a game changer. It's changing how people are looking at it. The safety has been really dialed into SMRs. That's the thing. There's been a lot of conception with SMRs that, okay, they're factory built. It's just going to kind of be, is the build quality going to go down over time? All of these things, but with the rigorous regulations that follow nuclear as it is, there is going to be nothing more than safety and all of those concerns dialed into the construction of those. So very interesting how SMRs are tipping the scale in the favor of nuclear so much. Because that's the big thing. You've got your large scale nuclear power, and then you've got your SMRs. I mean, it's the same technology, just in a whole different footprint, and a whole different cost level. It's just changing the market dynamically. So security and proliferation concerns. So there are many valid concerns, but they are manageable. I mean, there are many concerns that go along with nuclear power. The International Atomic Energy Agency, or also IAEA, sorry, excuse me, monitors nuclear fuel cycles and works to assist plants with much needed hardening against potential threats. So it's not just the companies that are working at it. You have, the International Atomic Energy Agency, you have OSHA, you have, the Department of Energy. All of these players are working to make nuclear energy safe. There's been a lot of lessons learned, and unfortunately, they were not fun lessons to be learned, but they did happen. We did learn from them, and it's made us better today so that we can actually make this technology more viable and more safe and more readily available to add to the grid and to the growing demand. So today's advanced reactors often use proliferation resistant fuels. Across the world, many responsible nations are deploying and utilizing nuclear generation and are mandated to maintain strong controls. But yeah, they're definitely highly regulated. SMRs are going to be highly regulated. It's not like someone can just buy an SMR and go throw it in their backyard and say we're off to running. I mean, there's still stringent rules, procedures, laws, government overreach, all these things that will go into place with this as well. So it's not like SMRs are going to be anything that just anyone can go off and buy. There's definitely going to be a lot of regulations around them as well. But yeah, there are definitely security concerns. A lot of these things, like facility attacks. What happens if someone goes into the facility? Could they break through? There's a lot of those concerns. Could it be an unstable material? Like I said before, the uranium-235 that's used in power generation is nothing like the uranium-235 or the actual plutonium, which nuclear generation does not use plutonium whatsoever. Is a whole different animal. It's not enriched to the level of vulnerability. So, you blow up a nuclear power plant, you're not going to have a nuclear explosion. However, there is the radiation concern. I mean, there is that, and that's why the outer shell and a lot of the hardening with these nuclear is looking at bulletproof. They're making these systems where they are ultimately impenetrable. Like a lot of the nuclear reactors, the concrete outside walls, they're so thick. I mean, it would take. I mean, they're just making them where attacks are slim to none. I'm not saying they couldn't happen, but yeah, there's a lot of safety, not just in the actual fission and reaction itself, but within the facility, within physical security, cyber security, all of these different things. And that's another thing, with the growing technology, we have growing concerns with cyber technology, and that's another thing that that nuclear is taking into consideration as well. With technology advance, you also come with technology risks. So there's give and take there. But yeah, there are concerns. There always is going to be concerns. There's always going to be risks. But industry has done a great job in managing those risks and putting as many controls in place to mitigate those to as minimal as possible. So environmental and ecological impacts. The nuclear cooling processes use water, but far less than that of a coal power plant per kilowatt hour in many cases. With the introduction of a closed loop system, this drastically helps to reduce the usage and impact. Thermal plumes are also heavily regulated. The uranium mining footprint is relatively tiny due to uranium's energy density, so you don't need to mine it as heavily as you do coal. Nuclear's total ecological effect is very low in comparison to other sources of energy. So coal mines are way bigger than uranium mines. Nuclear power does not take the amount of water that a coal-fired power plant does. You know, those kind of things. And with SMRs, it's just everything's just taken into a smaller account. And most of them are actually condensed systems where they have the water internally, those kind of things. So it's a lot of different things, a lot of cool technologies. And like I said, we could spend a whole nother presentation on SMRs just themselves because the technology is so great and so interesting. And if that's something you want to do, we could definitely look into doing an SMR presentation as well. So just let Sarah or myself know, and I'm more than happy to do that. Okay, so addressing common myths. There's a lot of myths that surround nuclear power, like the glowing green barrels and, all of these things. There are many myths that persist around nuclear energy. However, the scientific data has proven to counter these myths. Nuclear waste is handled and managed extremely safe. Nuclear safety record is excellent with the fewest deaths, including Chernobyl and Fukushima. You don't want deaths at all, but within those major accidents, there were still minimal. Education around nuclear energy has helped dispel the fears and the public perception to clear the muddy waters surrounding it. That's the big thing, is a lot of education. There's just been so much negative perception about nuclear power over the years that it's hard to get the public perception to be more accepting of it. However, the tide is changing to where nuclear is becoming more of a positive look. They're seeing way more of the benefits than the cons. And like I said, SMRs have changed that. I mean, the technology's changed it. The safety technology has changed it. Technology as a whole has changed it. Nuclear waste is unmanageable. The fact is that small contained repositories are advancing. Those are the things. The myth is the higher radiation risk. The fact is public exposure is lower than coal pollution. It's true. It's been looked into. The myth is unsafe overall. The fact is it's the lowest death per terawatt hour of any source. And these are data-driven facts checking this. So, I mean, it's been looked at by the EPA. It's been looked at by the International Atomic Association, IPCC. These are things that are looked at. Like cooling towers on the nuclear power plants. They see a lot of perception is that steam is just radiation. There's no radiation coming from those cooling towers. It's just cooling water. That's all it is. And they have systems in there checking to make sure, and there's been no sign of radioactive water in those. It's just steam. That's all it is. So kind of interesting. That's something that, learning about nuclear technology, I never really understood. I was like, because I kind of thought the same thing, is that water radioactive? But there is such a stringent controls on environmental impacts when it comes to nuclear that they are being tested. Those cooling towers have monitors on them 24 hours a day reading all of the input. They have scientists, environmental engineers, everyone on site monitoring that so heavily. I mean, it's incredible how heavily they're monitoring these systems. All right, so the growth projections. The International Energy Agency, the IEA, and the International Atomic Energy's net zero scenarios project that nuclear generation doubling throughout the world or more by the year 2050. I mean, that's their main. These are studies. I mean, I mentioned it in previous slides. These are studies that are real studies that have been put in. A lot of time, a lot of energy has been put into this. So nuclear power and interest is definitely growing. Projects show a high case scenario of over 990 gigawatts at the high side. Nuclear growth hinges on public policy and from growing tech deployment. So yes, these are the predictions, but there is, it's liquid to a point. There is vulnerability with that, depending on how stringent policies are. Does tech deployment slow down? It's not going to go away, but does it slow down to where the peak isn't growing at 4%? The demand isn't growing at 4% every year. I doubt it, but these are things that could definitely take place. So the statistics are realistic, and these are a realistic projection with current momentum that we are seeing throughout the world today. So this has looked at how things have been growing today as well as the future, as well as what's happened in the past. I mean, and it's no surprise that the demand for energy is growing rapidly. And with the declining of fossil fuels and other sources of generation, plus, not just taking them offline, a lot of these older fossil fuel generation plants are they're meeting their end of life for a lot of them. I mean, stuff breaks, things wear out over time, and it's coming to the point: do we rebuild? Do we put the end back into this, or do we look at moving over to a newer technology such as SMRs and those kinds of, these are discussions that the companies and industry is having daily. It's that cost debate that I showed you on a couple slides ago. It's that cost debate, and it's really happening. It's happening constantly throughout the industry as these plants are aging, coming offline. New companies are coming online, wanting to get into the energy sector. And SMRs are also getting. I mean, they're becoming something that could potentially be something that a startup generation facility could latch onto and start, putting out there. So kind of interesting. It's really fun to think about, and it's really cool to see things changing and how positive nuclear is looking. Okay, so today's technology roadmap. So in today's nuclear technology roadmap, small modular reactors will start to be deployed first. That's the first new technology that's going to be sent out first. Proposed locations have already been in the works throughout the United States, Canada, and Europe, while new experimental Gen 4 and ATF reactors are slated for the next decade, if everything stays on track with fusion and the technology continues to advance the way it has. The roadmap shows incremental and transformative advances which will enable rapid scale up. So I mean, it's just interesting, how much things have changed. And with the SMRs, for instance, I live in Utah, and it was brought out about 6 months ago that Brigham City, Utah is looking at becoming one of the first places in the Western United States to put SMRs in. So it'll be interesting to see. Canada's been heavily engaged in bringing SMRs into their country. I mean, it's definitely something that's happening. The technology is there. The technology has been proven. So, whether or not it moves forward is kind of based on public perception and viability, costs, as well as environmental impacts and policies. I mean, those are the big thing: licensures, policies, impacts. I mean, there's a lot of red tape that still needs to be cut through that luckily world governments are kind of looking into a little differently now. Which they did put that in good measure, for safety measure to start with. And I think that it has done nothing but help to make nuclear power more viable, more safe. And it's also made the wheels spin with all these smart people to create something like an SMR, taking the technology that's in the ships, the aircraft carriers and submarines, and looking at that as maybe a viable source for power generation. So really interesting, really cool. So policy and requirements for growth. I kind of mentioned this in the previous slide, but for nuclear to really take hold, governments must work to accelerate approvals without compromising safety. There needs to be work to de-risk financial burdens and build public trust throughout transparent scientific facts. Also, there needs to be work to foster global standards for supply chains and tech globally. So, I mean, that's the big thing for it really to take hold. There needs, this red tape is there's still a lot of red tape, and, they need to figure out making things run a little bit smoother, a little quicker, making the licensure and procedure process, getting the permits faster than they are now. Because right now it's a really lengthy, long process, even though a lot of the regulations have been lessened due to the SMR technology and governments wanting to explore this technology as a viable source. It'll be interesting to see how rapid things can take off when as governments start looking more and more into it. All right, so opportunities and investments. Nuclear is back in the conversation, and they're and here to stay when it comes to viable sources of generation. With the advancements made with small modular reactors and increased safety measures, nuclear offers a huge market with new builds, life extensions, and technology. Private investments are rising with big tech and manufacturing buying into the technology as a solution to their power-hungry AI and data centers, primarily in the United States, Asia, and Europe. Additionally, with the decline of fossil fuel generation, nuclear is the only viable solution to ensure a strong and dependent baseload. Nuclear also helps with climate initiatives globally and ties directly into the net zero goals. So market growth, it's growing. I mean, it's planned to go over $1 trillion. Private sector surge, tech firms, utilities, SMR, they're advancing supply chains, jobs. There's so many different job advancements, and investments are being made across the US, Asia, and Europe as the main sources of giant power demand. Oh, all right. We're running out of time. I apologize. We're about done though. So the key takeaways. So nuclear is quickly resurging because it uniquely solves multiple energy concerns that we have today by providing a low carbon base load at scale. So it's scalable. I mean, these are the things that it's scalable. It can be added. Grid stability and energy independence. Advantages of nuclear energy are clear in data and scientific analysis. Challenges like cost and perception are being tackled. Nuclear fits perfectly with renewables to provide affordable and reliable transitions from fossil fuels. The overall outlook. Excuse me, I apologize. The overall outlook is bright for nuclear energy if policies enable it, which we have seen in the United States, Asia, and Europe, and several other countries who are working to deregulate based off of the need for more reliable generation, and demand continues to grow every year with no signs of slowing, as well as to take note that there are a lot of fossil fuel facilities within these major countries who are coming to end of life and major decisions need to be made. So the role of nuclear in tomorrow's world and the call to action. So nuclear will be an indispensable asset in tomorrow's world by providing the firm backbone for massive clean electrification globally. A diverse energy portfolio will win every time. And this is the big thing. If nuclear technology is growing, the interest is growing, the demand is growing. Things are definitely looking way more bright for nuclear generation than they did a decade ago. There's been a lot of different technology advancements that have taken place, a lot of different perceptions, a lot of different costs. The technology of SMRs, really have pushed technology really into the forefront. That technology has been groundbreaking for making nuclear even something looked at again, because it used to just be overshadowed not only by the public perception of fear, but the overall cost to build a large nuclear facility was pretty much astronomical compared to other sources due to the safety concerns, the regulations. The plants, nuclear power plants have to definitely be built to a lot higher standards than like a coal or natural gas facility. Can't just be erected, over time. There's so many environmental impacts, different fees, different license. That's the thing. It's if you wanted to build one and you're looking, you should plan for, 5 to 10 years down the road to even get your permitting. Then you need to rebid it. Then you'll find out the costs are are higher or different. Maybe the materials that you looked at before are different and changing. So it's just been a really long, hard struggle. Not saying it couldn't be done. It's just been a long, hard, super expensive struggle to build a nuclear power plant, that it's just really not been done too much. Like the one in Georgia was the most recent one, and they started working on that years ago. But I think with the growing demand, the SMR technology, getting the Gen 2 and Gen 3 reactors, I mean, those by themselves are more simplified, they're safer, and they're going to be a lot more cost effective to build, even though there's still nothing like an SMR, which is going to be scalable. I mean, SMRs are definitely going to change the world. I truly believe that, and I truly think that we're going to be seeing SMRs taking hold within the next 10 years for sure. You know, the big thing is it's secure, it's low carbon, it's reliable. It provides a wonderful base load. It's just a wonderful source of energy, and we have it. We have the technology, we have the energy, so why not use it? And that's really where things are kind of getting pushed towards. It's like, okay, we have the demand, we have the technology. We need to figure out a way to use the technology that allows public perception to be more on board, as well as creating a viable source for generators, so it doesn't break the bank to create them. And then, yeah, it's just a great source of energy and great source of power generation that is needed not only in the United States but globally. Um, yeah, that's it. I really appreciate it. I know we didn't leave a lot of time for questions, but there's my email address. Please email me with any questions you have, or reach out to Sarah. More than happy to answer those questions. I know that there are a lot of the questions around nuclear are pretty complex, a lot of in-depth questions. And like I said, if there's things in this slide that you saw that you were interested in learning more about, let us know. I'd be more than happy to do another presentation just on SMRs, costs, energy impact, licensure. I mean, we covered a lot of stuff at a very high level that we could definitely dive way more into. This was kind of more of a high level to let you know why nuclear energy is becoming more and more the interest in it is growing, why it's coming back to the forefront in energy talks for demand. So thank you so much. I really do appreciate you all joining, and I hope he's able to get something from this. But yeah, please reach out with any questions that you have. I know we ran right up next to time, so I apologize on not being able to take questions right here at the end. But please, there's my email address. Please send me email. Reach out to Sarah. Yeah, we'll definitely get your questions answered. But I'll turn it over
And I
to
know
Sarah. Thank you.
we've got a couple questions in the chat from Mike and from Jill, so we will go ahead and send you an email with those responses since we are running up right against time. So again, if anybody has additional questions, feel free to type them in chat real quick before we end the meeting, or like Garrett said, you can email us and we can get back to you with those responses. And this recording will be made available, like I said earlier in the presentation, on our YouTube channel. It'll be later this week or early next week, and we appreciate everybody joining. So thanks a lot, everybody.